Hi, my name is Isabella Pereira, and I'll be discussing the paper Secure Healthcare Access Control System for Anomaly Detection and Enhanced Security in Cloud-Based Healthcare Applications. This paper fits into Category 1 of Access Control. First, why did I choose this paper? In my senior design class, I'm developing a web app to de identify data so medical professionals can share patient data with researchers while making sure that they're still in compliance with HIPAA. Throughout the research phase of my project, I learned about all the complexities that go into making sure patient data is secure. One thing that I started wondering about more and more in this process was how systems with patient portals are able to guarantee privacy. Another motivating factor for me was the cloud-based security aspect. Since anyone with a username and password can gain access to the system, and from virtually any device, I wanted to see what additional safeguards are needed and how they could be implemented. On to the summary now. The expansion of cloud based systems into the healthcare field poses a lot of new challenges to data security and privacy. So now it's especially important to have clear rules and protocols to make sure health information is sufficiently protected. This paper presents a framework with the goal of improving security and reducing delays in cloud based healthcare systems. Before creating this framework, however, the authors first compiled the data that they would be using in the testing phase later. They chose the MIMIC 3 dataset, which has records from about 50,000 ICU admissions between 2001 and 2012 from the Beth Israel Deaconess Medical Center. From there, it underwent pre processing, removing duplicates, and they standardized the units. Then the paper describes their proposed architecture, all of the requirements that they are originally setting out to make sure the data is secure. They went with some industry standards here, choosing to use TLS and AES encryption. TLS, or Transport Layer Security, is the protocol that's typically used to establish a secure session. TLS adds on to the TCP handshake, like you can see here in the lighter blue, and this authenticates the server with its public key and certificate, then having both the client and server exchange keys and decide on a cipher. It also uses AES encryption, which we know is a symmetric key algorithm. So to me, these authors chose this algorithm because it has higher diffusion. So we have a lot of transposed characters, but it doesn't necessarily need to provide authentication since they've already incorporated TLS. Then we move on to the algorithms they designed. They started by building off an RBAC, or role based access control scheme, and next was implementing multi factor authentication for users. The author suggests that users verify their identity with a smart card, some form of biometric data, like a fingerprint or an iris scan, and then their password. On to the RBAC from before. The authors add on fine grained access controls, where predetermined admin users can adjust permissions for a given person or role. If a user's access needs change for whatever reason, they leave the organization, they get promoted. We then have the access approval workflow, which is a chain of admin users that are in charge of processing new access requests, making sure that they are in line with both HIPAA and the organization's policies. Another important aspect here is logging. The system should log all of the high value operations like logins, changes in access control, and access requests. These logs are then monitored for any anomalies that would suggest that there is some malicious actor. In the event all these measures fail, we still have the data encryption and masking to help protect the more sensitive information. This section also specifies protocols for how to manage users, roles, and access control policies. Then it also outlines how to integrate SHACs with existing healthcare IT systems and electronic health record systems. In the results, analysis shows that Shax outperformed pure RBAC and ABAC schemes in several important measures. It performed better in terms of standard software metrics like throughput, scalability, and resource usage, but also in security specific metrics like resilience against breaches and ability to distinguish abnormal behavior. In terms of resilience, Shax had a 12.5% improvement over ABAC and a 10% improvement over RBAC. And as we can see in the ROC curve for anomaly detection, Shax had an area under the curve 15% greater than RBAC and 10% greater than ABAC. Overall, the paper found that Shax was a significant improvement, at least over these two. One way I thought to extend the framework in this paper was to introduce a quantum-resistant encryption scheme. While quantum computing, as we know, is still in its infancy, and we're still very far from a time where everyone will have their own personal quantum computer, the technology is here. And I don't think we're too far from seeing these time consuming but otherwise simple encryption algorithms like RSA be easily broken, regardless of how much we increase the key size. So instead of factoring prime numbers or performing matrix operations, lattice cryptography is based on the manipulation of vector sets, and when these problems start escalating to vectors in the hundreds of dimensions, these problems can get very complicated, so much so that we believe that these algorithms will be quantum resistant. And provided you have the key, lattice cryptography tends to be much more efficient and require less overhead compared to other quantum resistant algorithms. And personal health information is something that legally and morally needs to stay private. And those who want to break that privacy are everywhere, including the fields that would have easy access to a quantum computer the second it's able to break through classical encryption. So I believe lattice cryptography would be a good way to make sure that when that time comes, health information is already secured. What I found this paper does well is outlining a full comprehensive framework for a secure health app that includes error handling and steps for integration with other systems. I found the authors really keep a balance between both the theory behind everything they do and the algorithms that have real world applications. A lot of the attention to small details really comes through, and I feel like it would help reduce the complexity of implementing this. While the framework and the analysis were both very detailed, I noticed Shax hasn't really gotten to be deployed in any real world scenarios. All their analysis data was from only ICU patients and from only one medical center, so its performance hasn't really been tested with the large differences in the ways patient data can be documented. Also, while this framework has been shown in this case to outperform RBAC and ABAC, it was always under relatively low demand. So in the future, I would like to see if this could be tested against more real-world challenges. To conclude, I enjoyed this paper. I found the process really interesting, and I learned a lot. Here are the references to the papers that I used in my research, as well as the image sources.